Welcome everyone. So today we are tackling something huge.
Yeah, I've been looking forward to this one. Superconducting quantum computing.
Okay, look at this circuit. What are we actually seeing here?
Honestly, this is the architect's blueprint for the quantum realm. Every single line on there matters.
And I hear this little element in the middle is the real hero of the story.
The Josephson junction. Yeah. Everything we build in quantum hardware comes back to that one nonlinear component.
All right, let's walk people through it layer by layer, from the physics all the way up to a working processor. Before we dive in, I think we need to set the stage. How did we even get here?
Right, so for about a century, we rode Moore's law. Billions of transistors, all exploiting the bulk properties of semiconductors.
And it worked beautifully.
It did, until it didn't.
And Feynman saw this coming way back in 1982, right?
Exactly. He made a really simple argument. If you want to simulate a quantum system efficiently, your computer has to actually be quantum.
So it's not bigger silicon, it's a completely different paradigm.
A whole new philosophy. We stop shuffling electrons in bulk material, and we start engineering individual artificial atoms.
So what is a qubit? Let's start from the basics.
Okay, a classical bit boring. Simple 0 or 1.
And to describe n qubits classically, you need 2 to the n bits.
Which blows up fast. 50 qubits. More bits than atoms in a grain of sand.
But a qubit lives on this continuous surface, the Bloch sphere.
Yeah, and here's where people get it wrong. They think quantum speedup means trying all answers at once.
Oh, that's the pop science version, isn't it?
Totally. The real mechanism is interference. You engineer constructive and destructive interference between probability amplitudes, so the right answer survives and the wrong ones cancel out.
Subtle, but that's the whole game. Okay, so why do we specifically need a Josephson junction? Why not just a regular resonator?
Good question. A regular LC circuit has evenly spaced energy levels. Omega 0 to 1 equals omega 1 to 2.
And what's wrong with that?
If you try to drive the first transition, you also accidentally drive the second. You can't isolate two levels.
Oh, so you lose the qubit entirely.
Exactly. But with a Josephson junction, the potential becomes anharmonic. Levels spread out unequally.
And that uneven spacing is what lets you address just the bottom two.
That's the whole point. Nonlinearity isn't optional, it's the ingredient. Plus, we cool the whole thing to 10 millikelvin to kill thermal noise.
All right, let's zoom in on the junction itself. What is this thing actually doing?
It operates in the 1 to 10 gigahertz range, which is microwave territory.
Conveniently, the same band as our everyday electronics, right?
That's not a coincidence. It was engineered below the plasma frequency on purpose, so we can drive it with existing hardware.
And the physics?
2 equations. Current equals IC times sine of phi, and the phase evolves proportional to voltage.
Sine phi, that's where the nonlinearity comes from.
Right, and here's my favorite trick. Swap one junction for 2 in a loop, a squid.
And now you can tune the effective Josephson energy with a magnetic field.
On demand. That's huge for control.
So how do we actually get from a classical circuit to a quantum Hamiltonian? I always find this part mysterious.
It's really just 4 clean steps. First, identify the nodes, define the fluxes and charges.
Okay, just labeling the circuit.
Right. Then step 2, write down the Lagrangian capacitor energy minus inductor and junction energy.
Classical physics up to this point.
Completely classical. Step 3 is a Legendre transformation. That takes us to the Hamiltonian framework.
And then comes the magic step.
Yep, step 4, quantum promotion. Flux and charge become operators. You impose the commutator, and suddenly the whole circuit is quantum.
Beautifully clean. So when people first started building these things, How many flavors were there?
3 main ones, and each one leans on a different energy regime.
Let's start with the charge qubit.
Also called the Cooper pair box. You control it with voltage, and EJ is much less than EC, so charge is your good quantum number.
And its sweet spot.
NG equals plus or minus a half. That's where charge noise cancels out.
What about the flux qubit?
Opposite regime. EJ much bigger than EC, phase is well defined, and you tune it with magnetic flux.
And the phase qubit?
That one uses bias current and a tilted washboard potential. Interesting physics, but
Let me guess, no symmetry sweet spot, so noise kills it.
exactly, that's why it didn't survive.
Okay, this next slide is the slide, the one that changed everything.
Yeah, the Transmon really is the pivot point of the whole field.
So what did they actually change?
Almost embarrassingly simple. They just shunted the Cooper pair box with a big capacitor.
That's it.
That's it. But it shifts EJ over EC from around 1 to somewhere between 20 and 100.
And that changes the noise trade-off.
Dramatically. Charge noise immunity goes up exponentially, while anharmonicity only drops linearly.
Exponential gain for linear cost, that's a steal.
And the payoff? Coherence times jumped from nanoseconds to around 100 microseconds. Most of the industry runs on this architecture today.
But people didn't stop at the Transmon, right?
Oh no, the zoo just keeps growing. Let me walk you through a few.
Start with the quantronium.
Early variant, intermediate regime, pushed coherence to about 500 nanoseconds. Big deal at the time.
Then fluxonium.
Yeah, this one's wild. You shunt the junction with a superinductor made of dozens of larger junctions.
And the result?
Massive charge noise protection, high anharmonicity, and T1 past a millisecond.
Xmon and Gmon.
Transmon variants shaped like crosses, specifically designed for dense 2D grids.
And last one, Gateman.
Hybrid, semiconductor nanowire junction you tune with gate voltage, not magnetic flux. Much easier to integrate with control electronics.
Okay, scorecard time. Where does the hardware actually stand?
We check it against the 5-die Vincenzo criteria. That's the gold standard.
And the verdict?
4 out of 5, solidly. Scalable qubits, check. We lithographically print them on chips.
Initialization.
Check. Measurement projection, or environmental relaxation, resets the ground state.
Gates.
Check. Single qubit fidelity above 99.9%, 2 qubit above 99.
Readout.
Check. High fidelity Q&D dispersive measurement.
And the one that's still maturing.
Coherence times. T1 and T2 have climbed from nanoseconds to hundreds of microseconds, but we need more for full fault tolerance.
Still, the trend is clearly going the right way. Having good qubits is only half the battle, they have to interact.
Right, and we have a whole toolkit of 2-qubit gates.
What's the C0 approach?
Cross-resonance. You drive 1 qubit at its neighbor's frequency, and you get a conditional bit flip, no on-chip tuning required.
And the C phase?
That one's clever. It borrows the non-computational 0-2 state, briefly brings 1-1 into resonance with it, and picks up a conditional phase.
Without disturbing the other states.
Exactly. Then you've got I-swap, which directly swaps 0-1 and 1-0 and tacks on a factor of I.
And tunable bus coupling.
That's how you scale. You connect fixed-frequency qubits through a tunable coupler, and you can turn interactions on and off on demand.
Here's the paradox I always come back to. How do you measure a qubit without collapsing it?
You measure it indirectly. That's dispersive readout.
Indirectly how?
You detune the qubit far from a nearby resonator. There's no real energy exchange between them.
So they don't actually interact.
Not in the energy sense. but the capacitance between them causes a state-dependent frequency shift in the resonator.
Oh, so you probe the resonator, and the resonator's frequency tells you the qubit state.
Exactly. The qubit never gets measured directly. The only catch is that the shift is tiny, so you need Josephson parametric amplifiers to detect it.
Operating near the quantum noise limit, right?
Right at the edge. That's how we get single-shot, non-destructive readout.
Okay, this is the part that kept quantum computing stuck for decades. Error correction.
Yeah, and I want to explain why it's uniquely hard.
Go for it.
3 obstacles. 1, no cloning. You can't copy a quantum state and keep a backup.
Unlike classical bits.
Exactly. 2, measurement destroys superposition, so you can't just peek at your qubit to check for errors.
And the third.
Errors aren't discrete flips. They're continuous angular drifts on the Bloch sphere, way harder to detect.
So how did people solve it?
Brilliantly, they used entanglement. You don't measure the data qubit, you entangle it with ancillas, then measure the parity of the ancillas.
Are these two in the same state or not? That kind of question.
Exactly. You learn there's an error and where without ever touching the data. Then a microwave pulse fixes it.
Now let's scale that idea up. This is the surface code.
Imagine a 2-dimensional grid of qubits with nearest neighbor couplings.
And half of them are doing the actual computation.
Right, those are data qubits. The other half are measure qubits.
Are the measure qubits just sitting there?
No, they're constantly working. Each one performs a 4-qubit parity check on its neighbors via C0 gates, non-stop.
And out of all that activity,
You get a single logical qubit. Dozens or hundreds of noisy physical qubits cooperating to simulate one very stable one.
and as the grid grows, the error rate goes down.
That's the whole point of fault tolerance.
Let's talk about something really surprising, how these circuits interact with light.
So in nature, atoms and photons interact weakly. Coupling strength scales as alpha to the 3 halves.
Which is a tiny number.
Very tiny. But superconducting artificial atoms completely flip that, coupling scales as alpha to the 1/2, or even inverse square root.
So stronger, not weaker.
Way stronger. We can reach ultra-strong and even deep-strong coupling regimes, where excitations get swapped faster than decoherence sets in.
And that changes the physics.
Completely. Standard optical approximations just break down.
What happens instead?
You get bound virtual excitations in the ground state, exotic multi-photon interactions that literally don't exist in natural systems.
All right, now here's something that blew my mind when I first heard it.
The selection rules thing.
Yeah, nature has rules, and we get to break them.
So in atomic physics, photons only drive transitions between states of opposite parity. That's the strict rule.
Which gives you xi, v, and lambda configurations.
Exactly those 3, but no delta.
Why not?
Parity forbids it in natural atoms. But Josephson junction qubits don't have well-defined eigenstate parities.
So delta becomes possible.
And every transition is suddenly accessible, which opens real doors, on-chip photon amplification, direct microwave up and down conversion. Stuff you can't do with real atoms.
Okay, this next concept has the weirdest name on the whole deck, giant atom.
Yeah, and it's literal.
Wait, literally giant.
Compared to the wavelengths it interacts with, yes. A natural atom is basically a point, but a transmon coupled to surface acoustic waves is physically larger than the acoustic wavelengths it emits.
That sounds like it shouldn't be possible.
It breaks the dipole approximation completely. And because it's so big, it couples to the wave field at multiple points across the chip.
Multiple points, interesting.
And here's the most beautiful part. Space those points exactly half a wavelength apart, and the atom destructively interferes with its own emission,
Wait, it protects itself.
traps its own energy, cannot decay into the waveguide.
That is genuinely wild. One thing I want to emphasize, universal gates aren't the only path.
Absolutely. There's a whole family of quantum approaches beyond logic circuits.
Start with annealing.
Quantum annealing initializes the system warm and cools it adiabatically toward the ground state of a problem Hamiltonian.
And the qubits tunnel through barriers.
That's the trick. Tunneling lets them find solutions classical optimization would get stuck on.
Then there's analog simulation.
You use Josephson arrays to directly emulate physics we can't reach otherwise. Synthetic magnetic fields, fractional anyons, interacting photons.
And digital chemistry.
Variational quantum eigensolvers. You compute molecular ground states, and long-term, maybe simulate enzymes like nitrogenase.
Which would mean room temperature fertilizer production.
Completely different food economics for the whole world. That's the prize.
Okay, let's tie it all together.
5 layers, from abstract quantum mechanics down to a working computer.
Walk us through it one more time.
The bottom is physics, the Josephson junction.
Then the component layer, the transmon itself.
Above that, the hardware layer, the 2D surface code.
Which gives us logical qubits.
Error-corrected and stable. And on top, the application layer where drug discovery, cryptography, optimization all live.
And I think the real takeaway is this.
The hard part isn't theoretical physics anymore.
It's systems engineering. It's all about how we stack the pieces together.
Thanks so much for coming along on this journey with us.